Imagine trying to design, well, anything critical, a bridge, maybe an airplane wing, even just your car's engine without really knowing its weakest point, or how long it'll hold up before, things start to go wrong. The usual ways of finding this out, they're often slow, really slow, a huge bottleneck, actually. So today, we're diving deep into a pretty fascinating solution from material science. Our mission is to unpack how some advanced algorithms are revolutionizing how we spot material damage early on, making it faster, more objective, and honestly, just way more accessible for everyone involved in design.
Right. We're digging into a recent paper by DeAndrea and colleagues from 2025. It's titled Advanced Algorithms for Early Detection of First Damage During Static Tensile Tests.
Ah,
And what's really cool here, I think, is how they took this clever observation about how materials behave under stress, and they automated it. It really promises to shake up industrial design.
okay, let's unpack that. Why is understanding this material response to stress what engineers call fatigue, right?
Well,
Why is that such a tough nut to crack, such a persistent challenge?
well, fatigue assessment is just incredibly complex. You've got the material properties themselves, the environmental conditions, different types of loads. It all massively affects how long something lasts.
Yeah.
And the problem is, proving a material's fatigue life the traditional way involves a huge investment. It's a major hurdle.
Okay, when you say huge investment, what does that actually look like, say, for a company trying to, get a new product out there?
So according to the standards, things like ASTM E466, E606, you typically need an SN curve. And to get that, you're looking at 5 different load levels. And for each level, you need 5 separate test specimens.
Wow, 5 times 5, that's 25 tests.
Exactly, per material.
Hmm.
So it's a huge amount of time, a lot of material samples, and yeah, significant costs. We're often talking weeks, maybe even months of testing.
Just to understand one material's fatigue.
It's a massive commitment.
So how does that reality hit designers, the ones trying to innovate quickly in today's market?
Well, frankly, it often discourages them from even asking for detailed fatigue data because of that cost and time. In today's fast-paced world, we need reliable material infostatic and fatigue as quickly as possible. It directly impacts how fast and safe new products get to market. And ultimately, it affects the stuff you buy, its quality, and how long it lasts.
Right. So what if there was a shortcut? Could we use something like, I don't know, temperature changes? That sounds almost too simple, like a superpower for materials.
That's exactly the idea behind thermographic methods, or TMs. They're actually pretty well established now. Basically, they involve analyzing the energy a material releases, or absorbs, by watching its surface temperature during tests. You use an infrared camera for this.
So we're literally seeing the stress and the internal work through heat, like thermal vision for fatigue.
Precisely. Take the Risitano Thermographic Method, the RTM, that's pioneered by La Rosa and Risitano. What they do is monitor the surface temperature during actual fatigue tests, the cyclical ones. And they saw these 3 phases. First, the temperature goes up to a stable point, they call it IST, then it stays constant for a bit, then right before failure it climbs again. And the key insight was this: the fatigue limit. That's the stress level where that stable temperature increase, it's basically 0, negligible.
Ah, so no heat buildup means it can handle that stress indefinitely.
Essentially, yes.
Yeah.
It offers a path to quickly estimate fatigue limits with pretty good accuracy. It's getting ready to move from the lab into industry.
Okay, interesting. Now, the DeAndrea paper we're looking at, it focuses on an even more efficient approach, right? The Static Thermographic Method, or STM. What makes STM such a big step forward?
Yes, STM. Proposed by Risitano and Risitano back in 2013. It's really exciting because it lets us get a design parameter linked to that fatigue limit super fast. And it does this by analyzing the energy release during just a single monotonic quasi-static tensile test.
Okay, monotonic, quasi-static. So, just one slow, continuous pull on the material, not the back and forth cycling.
Exactly. No repeated stress cycles needed.
And the advantage is there, specifically for engineers needing quick answers.
Oh, they're enormous.
Yeah.
Instead of weeks of cycling tests with tons of samples, you can get crucial info about damage starting in just 1 day of testing. And you only need a few samples.
1 day versus weeks, that's huge.
It really is. You just watch the sample surface temperature during that single pull, and again, it reveals these 3 distinct thermal phases.
Okay, walk us through those phases. What's the story the material tells us with its temperature in this single test?
Right. So phase 1, as you start stretching it, the temperature actually drops slightly in a linear way. That's the thermoelastic effect Lord Kelvin talked about. Basically, it cools a tiny bit as it stretches elastically, like stretching a rubber band quickly. Sometimes you feel it cool. Same idea.
Oh, okay. Makes sense. Then phase 2.
Phase 2 is where it gets really interesting. The temperature trend stops being linear. It deviates.
Mhm.
And this is crucial. It signals the start of irreversible changes inside the material, the very first microdamage appearing. During this phase, the temperature hits a minimum point right around the material's yield stress, where it starts to permanently deform.
The point of no return, essentially.
Kind of, yeah. And then phase 3, after that minimum, the temperature shoots up exponentially right until the sample breaks. That's driven by all the plastic deformation generating heat.
So that specific point, that deviation between phase 1 and phase 2, that's the golden ticket. That tells you when damage actually starts.
Precisely. They estimate the limit stress, SWIM, right at that inflection point where the slope changes. Rizitano and Rizitano stated this is the stress level where that first micro damage pops up. It's a critical threshold for any designer.
That sounds incredibly powerful, super efficient. But there must have been a catch, right? If it's so good, why wasn't it everywhere immediately?
Yeah, there was a catch. The main limitation initially was analyzing the data. It was really subjective. It depended heavily on the operator's experience, their intuition, to pick out the exact point where phase I ends and phase 2 begins, especially with noisy signals from the camera or different material behaviors.
Ah, the human element, like trying to agree on the exact moment a kettle starts really boiling.
Exactly. That subjectivity was the hurdle. How do you make something so dependent on human judgment truly objective and reliable?
Which brings us perfectly to the DeAndrea paper. What was their goal here? How did they aim to tackle that subjectivity problem and make STM truly usable?
Their core goal was exactly that. Make the STM prediction objective, take the operator's experience out of the equation as much as possible. So it could be adopted easily, outside specialized research labs. They wanted to automatically pin down that critical limit stress.
And they developed an algorithm in Python to do this. Were they the first to try automating it?
No, there were previous attempts. Researchers like Colombo et al., Crisafulli et al., they'd used iterative algorithms, bilinear models, to find that inflection point. And they were effective to a degree. But they could still be thrown off by, signal noise, which you always get with IR cameras, environmental stuff, camera sensitivity.
So this new paper refined those ideas, made the automation more bulletproof.
Exactly. They proposed a robust algorithm. And crucially, it was specifically tailored to fit the theory and assumptions of STM itself. They didn't just grab a generic change point detection tool. They built something specifically for this job, considering all the nuances of the STM framework, like using a specialized wrench instead of an adjustable one, gets a better fit.
Okay, let's get into the weeds a bit. How does this clever algorithm actually find those phase transitions without an expert staring at a graph?
Right, so the approach they develop is designed to be totally operator independent. Since the test data is quite short, just one pull, it works iteratively, step by step. First step, clean the data. It filters out outliers, any weird spikes in the temperature readings, using a statistical method called the interquartile range, or IQR.
Okay, like removing static.
Pretty much.
Okay.
It sets a threshold, usually 1.5 times the IQR, and ignores anything outside that. So you're working with a cleaner signal.
Got it. Clean data first, then what?
Then it divides the clean temperature data into two chunks, two subsets. The first subset starts at a fixed point in time to avoid any noise right at the start of the test, and its end point is what changes in each loop, each iteration. The second subset starts right where the first one finishes, and it goes all the way to the minimum temperature point identified in phase 2.
And it keeps shifting that dividing line between the two chunks, moving it along the data.
Yes, exactly. In each iteration, it shifts that dividing point forward by one data point. It's like scanning along the curve. For every possible split, if it's a straight line, does a linear regression to the data points it thinks are phase 1 and another straight line for phase 2. Then it calculates where those two lines would intersect. And that intersection point gives an estimate for the limit stress for that specific iteration. It builds a two-line or bilinear model for every possible split point.
Okay, that iterative process sounds thorough. What's the biggest win with this approach compared to just, say, eyeballing it?
The key advantage, they state, is its ability to identify the point of slope change regardless of the material, making the algorithm material independent. That's huge. It means you could apply it to different plastics, metals, composites, whatever, without needing an expert to tweak it for each one. Saves time, reduces potential error.
Material independent, that's definitely powerful. But hang on, if it's doing this over and over for different dividing points, how does it know which iteration, which intersection point is the right one? The best estimate.
Good question. That's where the optimization comes in. It uses 3 different checks, 3 parameters, to judge how good each bilinear model is. Think of them as quality control checks. One looks at how well the overall two-line model fits the data points. Another checks how well each individual line fits its own section. The third one confirms that using two lines is actually better than just trying to fit one single straight line through all the data, proving that the kink is real.
So multiple checks happening simultaneously.
Right. Technically, they're called coefficients of determination, R-squared values for the bilinear model for the individual lines, and a comparison to a single line fit.
And the really clever part is how it uses these checks to zero in on the final answer.
Exactly. Initially, these three checks might give slightly different answers for the limit stress. They might point to slightly different split points as being best. So the algorithm goes into an optimization loop. It starts tightening that initial filter, the IQR threshold, remember the data cleaning. It makes it stricter, step by step. And it keeps reanalyzing the data, recalculating everything, until the limit stress values suggested by all three checking methods agree, until they converge on the same answer.
Wow, okay, so it forces itself to find a solution that satisfies all its own quality checks, like building in its own peer review.
That's a great way to put it. It's not just about being automated. It's about building in self-correction and consensus finding. That's what makes it so robust and objective. It really increases trust in the result.
Okay, that sounds incredibly solid in theory, but the proof is in the pudding, right? How well did this algorithm actually do when they tested it on real materials?
The results were really compelling. They tested it against the established RTM method, the cyclical fatigue one we talked about earlier, using the same materials. They used a couple of advanced plastics, nylon CF, and a PA12 from multi-jet fusion, and also a common stainless steel, AISI 316L. A good mix.
And the comparison, did the numbers from this new fast STM algorithm match up with the traditional, slower RTM results?
They were in good agreement, as the paper puts it. The percentage differences were actually remarkably low. For the nylon CF, the difference was just 2.6%. For the PA12 plastic, 5.1%. And for the steel, AISI 316L, it was a tiny 0.06% difference.
0.06%, that's incredibly close, especially for materials testing, where there's always some variability.
It is extremely close. It really validates the approach. Even with the inherent noise and material differences, the algorithm's optimization process clearly worked very well.
So does this mean engineers can confidently use these STM results obtained in just a day for actual design work, for fatigue applications?
That's the conclusion, yes. The strong correlation means these limit stress values from the automated STM are reliable enough for design. The algorithm consistently found values like around 30 MPa for both plastics and about 219 MPa for the steel, with reasonable standard deviations. And these lined up well with RTM and other literature data. So for you, the designer, or even just as a consumer, this means potentially more durable, reliable products developed faster. It means trusting the components in your world a bit more.
This is clearly a huge step forward, making material characterization so much faster and more objective. But what's next? Is the technology perfect, or are there still challenges, areas to improve?
Oh, absolutely. There's always room for improvement. While the bilinear model, the two straight lines, is great for spotting that first inflection point, it's still a simplification. It's not really designed to perfectly model the entire temperature curve, especially in phase 2, where the heat generated from damage can make the temperature rise nonlinearly.
So maybe more complex mathematical models could give an even richer picture of what's happening after the initial damage starts.
Potentially, yes. That's one avenue. And there are also certain types of materials that are still tricky for this current algorithm. Think about really brittle materials that break suddenly, or complex composites with multiple things happening internally at once, or even just testing at very high temperatures. These can create noisy signals, short signals, or overlapping heat events that are harder for the current algorithm to untangle.
Right. So how are they thinking about tackling those more complex cases, pushing the boundaries further?
Well, the future direction points towards machine learning. They're considering using ML-based classification techniques. These could potentially learn to distinguish between different overlapping thermal events or figure out how much heat is coming from the material versus the testing environment at high temps.
Okay, bringing in the AI.
Exactly. They're also looking at advanced, unsupervised learning methods, things like k-means, Gaussian mixture models, DBS scan. These kinds of techniques are good at finding patterns and clusters in data without being told exactly what to look for beforehand. So they might be better at finding those subtle transition points in noisy or complex signals.
That sounds really cutting edge, letting the AI find patterns humans might miss.
It is. And here's a neat idea. They might even use the current robust algorithm to automatically generate labeled data, identifying phase 1, phase 2, etc., to train future supervised machine learning models.
Ah, using today's breakthrough to bootstrap tomorrow's even smarter tools.
Precisely. It raises that big question, doesn't it? As materials get more advanced, how do our testing methods keep up? Integrating AI like this seems essential. It's truly forward-thinking.
Wow, what a journey we've taken. From the painstaking old ways to this AI-driven future. We started with those traditional fatigue tests, costly, slow, often a barrier to innovation. Then we saw the elegance of just watching temperature, using IR cameras to see stress with thermographic methods. And STM, the static method, offered this incredible leap of vital data in a day, not weeks.
But that initial subjectivity, relying on the expert's eye, was the bottleneck. The really groundbreaking thing from DeAndre and the team is this algorithm.
Yeah.
Robust, iterative, self-correcting. It objectively nails down that critical point of first damage, no matter the material, no matter the operator. That's the key takeaway.
And the impact. More reliable designs, definitely. Faster development, absolutely. Which ultimately means safer, more durable products for all of us. It's like finding a reliable shortcut to knowing if the materials around us are truly sound.
So maybe here's a thought to leave you with. Imagine a future where a completely new material, maybe some advanced composite, can be fully checked for its fatigue behavior in just one afternoon. Not by a specialist team after weeks of testing, but maybe by the designer themselves, using automated tools like this. How much faster could we innovate across every industry then? Aerospace, medical, consumer goods. What might that unlock?
A fascinating thought. Think about all the materials carrying loads around you right now. Thanks for joining us on this deep dive.